Okay, so we're back talking about meta-analysis of longitudinal time to event data today. Feel free to ask any questions along the way, and I'll take opportunities at different places to break and see if anyone has any questions. I guess before we get started, I could see if you have any questions from the get-go. Okay, it looks like there aren't any. And so let's go ahead and dive right into our lecture today. We'll give an example in just a minute about what exactly what we're referring to when we talk about time to event data. But I'll assume that at least at a high level, everyone has some concept of the kinds of data that we're talking about. And as really with any kind of meta-analysis, really the gold standard, the best approach that we can take for doing a meta-analysis of any kind of time to event data is using patient-level data. And typically in that context, if we're pooling multiple studies, when we have patient-level data, we'll be able to extract the most amount of information about drug effects or other kinds of covariate effects on the hazard of the event occurring. But there has been a literature developed primarily in the statistics literature around how to do meta-analysis when only aggregate data is available. And typically in that context, the analyses generally proceed in modeling the log hazard ratio, if we're using studies that have multiple treatment arms in them, possibly comparing differences in median endpoint values, like the median overall survival or median progression-free survival if we're working in oncology, where they may take, at particular time points, take estimated event rates. So you might take, for example, the estimated survival rate at 1 year or at 2 years. And all of those are reasonable things to do. What they do is they kind of shrink down that whole time to event distribution down to one summary measure, the log hazard ratio, or a median survival time, or a survival fraction at a particular time point. And so in that regard, we're missing out on some information that's in the data that are available to us. But they allow us to work within the context of the kinds of models that we've already worked with. So if we're working with log hazard ratios and their standard errors, then we can apply the kinds of traditional statistical approaches that we used at the very beginning of the semester. Similarly, if we're working with median endpoint values or fraction of patients surviving at a particular time point, we could use the kinds of binomial models. Of course, depending on the disease area that we're working in, all of your studies may be comparative studies, and so you can get something like a hazard ratio. But in some areas, like in oncology, there may be a number of single-arm studies or non-comparative studies that couldn't be used in that kind of analysis. So using something that's a comparative measure like a hazard ratio would involve us eliminating those studies from our analysis. And the other kinds of approaches using median survival times or survival rates at specific times, what those do is they limit us in the fact that we're considering specific kinds of outcomes independent of each other. So if we have a percent surviving at 1 year and a percent surviving at 2 years, those are typically done as two separate analyses. And that, again, sort of isn't utilizing all of the information that's really available in those time to event curves. The bonus, though, is that they're easy to implement. And so even though they're underutilizing data, they're easy to implement. The flip side is that there are methods that are not particularly hard to use, and we'll talk about those today, that do use more of the data and more of the data that's presented in the studies. And really the two basic approaches that we'll talk about today allow us to consider jointly modeling survival rates in treatment groups and in treatment arms and studies. So building parametric models that we'll talk about today for the survival rates, modeling those extracted time to event curves. So the kinds of data that we are presented with might look like this. So these are a pair of Kaplan-Meier curves that were extracted from an article in the Journal of Clinical Oncology in 2009. And this is, in fact, one of the studies that from a data set that we'll be looking at later on in the class, looking at the effects of thalidomide in addition to MP in multiple, I believe it was in multiple myeloma. And so what we have here is an estimate of the surviving fraction over time. And so you can imagine that there's quite a bit of information here rather than just, say, the median, which would be taking 1 point off of each of these curves, or taking a slice at a particular time point, like maybe at a 12-month time point, and making a comparison between the two treatments at different time points. What the methods that we'll be looking at today will allow us to take multiple time points across these curves and build models, parametric survival time models that account for the correlation over time within those time points, or model the numbers of patients that are having events in over particular designated time intervals. One of the other important things to notice about this plot is what is printed here at the bottom. And what this presents to us is the number of patients at risk at particular time points over the course of the study. So this will tell us that, for example, that 116 patients were at risk at time 0 in the placebo group. At the 6-month time point, there were 105 patients at risk. All right.
This actually should be.
Thanks, Joe. Okay, just let me know now if you guys can see the screen and hear me. You should be able to. All right, apologies for that. I guess I'm rusty getting back into the swing of the semester. Okay, so as I was saying when I was on mute, what you missed in terms of the video for slide 1 is I think I covered all of those points just in talking to those. Hopefully you're able to download the slides and you'll be able to read those at your leisure. For the second slide, what we're looking at is our example Kaplan-Meier curves, highlighting the fact that we have estimated survival, the surviving fraction over time, which is what the Kaplan-Meier estimator gives us. and highlighting the fact that in this particular publication, what they've provided for us are the number of patients at risk at particular time points over the duration of follow-up. So in the placebo group, we start out with 116 patients at risk. At the 6-month time point, we've had some patients drop out and some patients have had events, and so only 105 patients are at risk at 6 months. As we get on to 12 months, 96 patients are at risk, and so on out to the end of the study where only 11 patients were at risk for dying. And that's going to be important as we talk about some of the methods for analyzing these data, is being able to keep track of the number of patients that are at risk for an event over the duration of the study. Okay, let's just check to make sure that everything is going okay. All right, so I'll just go ahead and shift back here to full screen mode. Okay. All right, so that's an example Kaplan-Meier curve, and that's the kind of data that we're going to be talking about modeling data extracted from these kinds of Kaplan-Meier curves. So what I've done is I think there's really two groups of approaches that have been described in the statistics literature, primarily around how to model these kinds of data. The first class of models these observed survival rates directly. That is, we're modeling these curves here directly. And there's really two important references in that regard. One is by Keith Deer, that was published in Biometrics in 1994. And the other is by Lydia Ahrens, published in Statistics in Medicine in 2008. In that paper, Ahrens and colleagues really expand on the approach that Deer set out in his initial paper. And so we'll talk through the key features of those and then step through how to fit those models in WinBUGS. Then the second class of models, rather than modeling the observed survival rates directly, model the survival rates, but the way that they come into play is in modeling the number of events that are happening over distinct time intervals. And there are really two papers that came out over the last couple of years that are related to that approach. One in Research Synthesis Methods and one in BMC Medical Research Methodology. The difference really between these two approaches is that the first paper uses parametric survival curves, and we'll focus on using those in our analysis as well. And the second approach talks about using semi-parametric or fractional polynomial models to describe the underlying hazard functions. Similarly, the models of Deer are really more like ANOVA kinds of models over time, and Ahrens and colleagues extend those to using parametric survival models. Or that's the kind of approach that they outline in their paper, are parametric survival models, but it's not restricted to that. So what we'll do is over the next hour and a half or so is step through both of these kinds of approaches, talk about the theory, look at some examples of how to fit those using WinBUGS. So we'll start with the model of Deer. And so I'll have to define a little bit of notation here. So we'll let Sijk be the true survival probability in treatment arm J in study I at the kth time point. And we'll assume that we have estimates. These could be Kaplan-Meier estimates, S hat Ijk, along with the corresponding standard error. So that's our data, the S hat Ijk and the standard error of S hat. And S hat is an estimate of S. And so what Deer said is, let's fit a linear regression model that relates the S hat to both between and within study covariates. And the within study covariate might be something like time. Between study covariate might be like a study effect. Could be treatment characteristics, could be either within or between study covariate, and possibly some interactions. And so he says, well, we'll fit a model that says the observed data, S hat, Now this S hat I here is a vector of across all observations within all treatment arms. Follows some linear model. That's a linear combination of the covariates xi and so has some residual vector epsilon I. And we'll say that the epsilon i's, this vector of epsilon i's, follows a multivariate normal distribution that's centered at 0 with some variance covariance matrix V sub I. And the important piece about his paper was that he was able to recognize that VI has some particular structure. And that the structure depends on the standard errors and the survival probabilities. And in particular, in order to calculate what the correlation between any two observations is, he works through some of the theory, and we can maybe talk about that in the lab meeting if people are interested in going through that part of it. But he works out the fact that the correlation between any two survival probabilities on those Kaplan-Meier estimates at 2 times Tijk and Tijl, where the kth time point is bigger than the lth time point, looks like this. It's the square root of Sijk times 1 minus Sijl divided by 1 minus Sijk times Sijl. So you can look at this. Here we have Sijk, 1 minus Sijk. That's like the odds of the event happening at the kth time point divided by the odds of the event happening at the lth time point. And so that's important because then we can derive what the variance covariance matrix looks like, because we know that at any time point, the variance of that of the S hat is just going to be the squared standard error, which we have in our data set. So we can use those elements to fully construct what each of the VI matrices is. And so what that allows him to do with his methodology is to say, well, we'll fit this model iteratively. We'll start by plugging in the observed survival proportions into to get us some approximation of the correlations and therefore an approximation to VI. And then given those VI, we can use a generalized least squares to estimate the theta, which is our covariate effects. And then given that estimate of theta, we can get predicted values of the S's, which can give us we can use to update our correlations, and then update the variance covariance matrix, and then recompute using generalized least squares our estimate of theta, and then iterate that procedure until we get to some convergence on our estimates of the covariate effects. And that's really what his paper talks about. And what you want to keep in mind is to me, the fundamental importance of what we'll be doing is recognizing the structure of this variance matrix VI, in particular, what the correlation between two observed or estimated survival times are at 2 time points. And so if we look a little bit at what this correlation is telling us, this tells us that if we have at 2 time points the survival times are similar, then this correlation is going to be something very close to 1. And if those survival probabilities are very different from each other, that correlation is going to get closer and closer to 0. So if we think back to our Kaplan-Meier curves, that would mean that if we were to take observations at, say, 6 months, and then take another reading off this curve at 7 months, the curve hasn't really dropped very much. And so those two observations are going to be very highly correlated, which means that if we were to extract lots and lots of data points off of this plot, we'd expect to have very highly correlated pieces of information. So we wouldn't have, if we were to extract 30 maybe observations off of these Kaplan-Meier curves, we're not going to have 30 independent pieces of information because of the positive correlation. So that's the estimate of deer. The other thing to point out in his models, he models the S hats as a linear function of covariates, in particular a linear function of time. And so what Lydia Ahrens did in her paper, she extended this approach that Keith Deere put together in a number of important ways. First, she extended it to use a mixed effects model structure. So we can put in some random study level effects, for example. She transformed the survival probabilities from a linear relationship to a transform scale that moves away things from the 0-1 scale to a minus infinity to infinity scale. So we now are able to more appropriately model the survival probabilities. And then in addition, she focused on using parametric models for the effects of time and covariates, as opposed to using that sort of ANOVA style approach that Deere used. So this is the model that they propose in their paper. So the transformation of the data that they use is the log minus log transformation. So if you imagine you have an observed survival time that's close to 1, then the log of that will be close to 0, and the log of that number that's close to 0 is going to be something that's close. It's going to be a large negative number. So as s gets closer and closer to 1, this transformed value gets closer and closer to minus infinity. And similarly, as s gets close to 0, the log of 0 goes to something like minus infinity, and the log of minus infinity gets to be closer and closer to infinity. So as s hat gets closer and closer to 0, this transform value gets closer and closer to infinity. So big numbers on the transform scale correspond to small probabilities, and large negative numbers on the transform scale correspond to large probabilities. So on this transform scale, she then says, let's model it as a linear function of covariates x and some random effects eta. And we'll say that the random effects have a distribution. Again, here I is denoting study. So the random effects from study I follow a normal distribution with mean 0 and variance covariance matrix omega. And again, the residual epsilon is this vector that follows a normal distribution, a multivariate normal distribution with mean 0 and variance covariance matrix VI. Now, VI has a slightly different structure because we're working on this transform scale. And so it's fairly straightforward to show that if you can use the delta method to approximate what the residual variance of this transformed response should be. And it looks like the IJ, or in this case, I should say the KL element of that matrix looks like this. Again, the correlation piece here in the middle is the same as we had before. But now rather than multiplying simply by the standard error of the kth element in the elf observation, we multiply by some function of that. That's the standard error divided by s hat times the log of s hat, both at the kth time point and then over here at the elfth time point. And that transformation comes in simply as an approximation to what the variance should be on the log minus log scale. And then in their paper, what they say is then everything else is just like you would do in the Deere approach. You would get an initial estimate for what your variance matrix V is. You can then use weighted least squares, or in their case, they fit everything using SAS. So they would use proc mixed to update estimates of the thetas and etas. Given estimates of thetas and etas, you get updated estimates of your survival probabilities, which gives you updated estimates of the VIs, and then you just continue to iterate the process that way. And so in order to fit these models, what we have to be able to do is have something that can fix this residual standard error variance in the estimation process. So we have to be able to fix VI. And then obtain sort of the fitted survival estimates, the predicted survival time, so that we can then update that VI matrix. And so if we were going to take this approach using SAS, you might write a macro, for example, that fits a model, extracts the parameter estimates, calculates those V's, maybe outputs those to a data set, and uses those as input into the next iteration of the estimation procedure. With the software that we're using for this class, we're a little bit limited though. We can't do that kind of exact procedure in the LME function in R because the residual error variance can't be fixed. You can fix it up to a proportionality constant, but you can't fix it completely. And I think we could conceivably do it in some combination of R and non-mem, but it would be a matter of sort of fitting something in non-mem, outputting results, doing some data manipulation in R, refitting the model back and forth. And in fact, doing this exact same iterative procedure in WinBUGS is difficult, but what I'll show you how to do is to fit kind of a related version of the model using WinBUGS. But there's a little bit of a rub here, because in order to fit models using these approaches, we have to have that standard error of those survival probabilities. And sometimes those are reported. For example, there may be a confidence interval that's given around the estimated Kaplan-Meier curves. And from that, if we were to digitize those figures, we could read off the confidence interval values at the time points of interest, and then we can derive the standard errors from those. It's not that often that we get confidence intervals published, and so we're often limited in terms of how we're able to actually extract the standard errors for our Kaplan-Meier estimates. But we can do a little bit of additional approximation based on what the survival curve is and the number of patients that are at risk. And so what I'll do is I'll step through some very simplistic ways to do that and some heuristic sort of ways about how we might get at approximating that standard error if we don't have those kind of confidence intervals or any more direct way of getting the standard error of the Kaplan-Meier estimates. So if we were in a perfect world where there was no censoring, so that means there's no patients dropping out or dropping out of the risk set over time, then other than for having an event, then it's pretty simple to show that the variance of our estimate of the survival curve is just equal to that estimate times 1 minus the estimate of the survival curve divided by n, where n is the number of patients in the treatment group at the start of the study. And we almost always get this n, number of patients in each treatment group at the beginning of the study. And because we have Kaplan-Meier estimates of the survival curve, we could actually derive this variance. And if we take the square root of that, that gives us our standard error. So if we have a small amount of censoring, this actually probably provides a reasonably good approximation to what the standard error is at any time point. But if you're working in a disease area where you have a lot of censoring, this is going to underestimate the variance because the number of patients at risk is decreasing over time, and so the variance should be getting bigger faster than it would be than this approximation would provide for us. So we need to think about alternative approaches to estimating that standard error, or else use this standard error, but just acknowledge that there's some that we're underestimating the true amount of the true standard errors. So if we're going to use a different approximation, we could go back to sort of first principles of survival analysis, which tells us that our estimate of the survival curve, S hat of t, is just e to the lambda hat of t, where lambda hat is the cumulative hazard. So that's the integrated hazard up to time point t. And we can use a delta method again to, given this relationship here, to get an approximation for the variance of S hat t. We can show that the variance of the estimated survival fraction is just that S hat of t squared times the variance of lambda hat of t, the variance of the cumulative hazard up to time point t. And there's been, and we can know from looking at the survival literature that we can approximate the variance of the cumulative hazard as the sum of these ratios, the number of events that happen at a particular time point divided by the number at risk at that time point squared. And this is the kind of standard kind of way to get standard errors and confidence intervals for Kaplan-Meier estimators. Of course, if we have the patient level data, we can calculate this kind of thing directly. But of course, we're trying to extract this kind of information from Kaplan-Meier curves. And so this notion about the number at risk at various time points over time that can be published at the bottom of those Kaplan-Meier curves can become really vitally important for us in estimating these, the variance of the cumulative hazard function, and which we can then translate into the variance of the Kaplan-Meier estimator. And there are some methods provided to talk about how to approximate this number of risk, a number of patients at risk over any time interval in the paper by Parmar and colleagues. And actually, there's a paper that came out just recently about, I can't remember if it was the end of 2012 or earlier this year, that also gives us sort of a different approach, and I provide the reference later on in the lecture today. But you can imagine now if we were to chop up our time interval into a number of discrete, non-overlapping intervals, we could approximate the number of events in that interval and the number of patients at risk in that time interval to get an approximation to the variance of the Kaplan-Meier function at that time point. So this is one of the issues with using this Deer-Ahrens approach, is we need to have these standard errors. You can do this more complex approach if you have a lot of censoring, or you could use a fairly simplistic approximation if you think the amount of censoring is small. So why don't I stop there and see if there are any questions before we move into the example. Okay, doesn't look like we have any questions. So the example that we'll use is taken straight from the paper by Deer. And the data were originally published a year before in a paper by Fine and colleagues. And they come from a meta-analysis of 17 randomized controlled trials that looked at the effect of a combination of chemotherapy and radiotherapy in postoperative malignant glioma. So all of these studies compared radiotherapy alone to radiotherapy plus chemotherapy. And the outcome was overall survival. And for this particular data set, what they did is they extracted the survival probabilities at 6 months, 12 months, 18 months, and 24 months after surgery. And so this is what the data look like from that paper. So if we look here, say at study 1 down here in the lower left-hand corner, this is plotted on the y-axis is the percent surviving. Plotted on the x-axis is the time in months. And you can see here at 6, 12, 18, and 24 months, we have our estimates pulled off of those Kaplan-Meier curves. The blue curves here in all of these plots correspond to the radiotherapy alone, and the red curves correspond to the radiotherapy plus chemotherapy. So for all these, or almost all of these studies, we have all 4 time points extracted. For some reason, in study 17, they only were able to extract data at the 12 and 24 month time points. Could be because those were just reported in a table rather than in a figure. I'm not sure. But if we were to look at this, kind of just qualitatively looking at it, it looks generally like in some studies, like this study here, number 2, radiotherapy plus chemotherapy seems to confer some benefit to survival. That's maybe the largest benefit. Study 9 also seems to have some benefit, as well as study 14. Some of the other studies have smaller, more modest benefits, like studies 11, 12, 13, 6. And some studies show them to be really pretty much equivalent, like study 16 or study 17. So we have some clearly there might be some between study variability here in the effect of chemotherapy in addition to radiotherapy. So to start with, what we'll do is we'll fit a model that assumes that the survival probability follows an exponential distribution, and will allow for some between study variability in the underlying event rates. So specifically, we'll say that the true survival probability in study I, in treatment group G, at time point t, is e to the minus lambda ig times t. So lambda ig is the rate constant in group G in study I. And we'll build a model for that says that the log of lambda ig is equal to mu I plus delta I times an indicator for G, the treatment group being the radiotherapy plus chemotherapy group, or RC. So another way to think about this is that the log event rate in the radiotherapy alone group in study I is mu I, and the log of the event rate in the radio chemo group is mu I plus delta I. And we'll say that those mu I's, the log event rates in the radiotherapy groups in the studies come from a normal distribution that has some overall mean mu bar, some between study variability omega squared mu. And similarly, we'll say that the delta I's, which correspond to the log hazard ratios in this particular model, also follow a normal distribution with some overall mean delta I, or delta bar, and between study variance omega squared delta. So that's the model that we'll be fitting to the data. Where this is the model that defines our survival probabilities over time. The model for the observed values, the data, if you will, rather than using the log minus log transformation that was used by Ahrens and colleagues, we'll use a logit transformation. Again, that transformation transforms that 0-1 scale to a minus infinity to infinity scale. It turns out that's probably we may just as well have used the log minus log transformation. This seems like to me a transformation that's maybe more familiar to those of us in pharmacometrics, and in fact is a more numerically stable transformation as we work with it within WinBUGS. So now we're saying our model here is that the logit of the S hats are equal to the logit of the S values plus a residual epsilon ij So just again, our notation here is that the observed survival observed survival fraction in study I, group G at time Tij is equal to the logit of the true survival surviving fraction in study I, treatment group G at time Tij plus a residual. And again, if we string out those residuals over time within a treatment group and within a study, we can go back to those sort of principles, same first principles that Deere and Ahrens put together, and we can derive what the model for VIG is. So VIG is now our variance covariance matrix for observations within the treatment group G and study I. Again, that's going to be VIG here, the way I've defined it isn't really block diagonal. VIG is a sort of full block matrix, if you will. Now, again, the correlations are the same as we had before, but now the variance terms are going to depend on the standard error divided by the square root of S hat ijk times 1 minus S hat ijk. And so the fundamental difference here between what was done in the Ahrens paper is that, I'm using the logit transformation rather than the log minus log. And there's one other important difference that is maybe subtle when you're just looking at these slides, is that I've replaced the S hats here in this middle term I replaced the S's in the middle term with S hats. So what that means is the way that I'm approaching this model is this variance covariance matrix, or the elements in these VI matrices, are fixed and known at the beginning. I'm not updating these in the estimation process. And so you can think about that as then these VIs being sort of working correlation or working covariance matrices that are accounting for the roughly accounting for the correlation over time, but not quite as precisely as what the model might be projecting. But as long as we're getting reasonably good model fits, the S's that would be getting plugged in here to this middle term should be pretty close to the S hats. So the difference between those should be minimal. And then because we're going to fit this in a Bayesian framework, we need to have some prior distributions for the 4 parameters here in our model: mu bar, delta bar, omega mu, and omega delta. And so I chose the following priors, which on the scale that we're modeling are fairly non-informative prior distributions. So I say that the log event rate in the radiotherapy arms is the mean log event rate is normal with mean 0 and variance 100. The mean log hazard ratio is also mean with prior as a mean 0 and variance of 100. And then the between study standard deviations, I put a uniform distribution between 0 and 10. If you think about these, this is a normal distribution for the log event rate in the radiotherapy and the log hazard ratio of the normal 0 standard deviation of 10. And that's on the log scale. So that covers quite a wide range on the log scale. And these between study variances are also on the between study standard deviations are also on the log scale. And again, we're allowing that standard deviation to go up to as much as 10, which is quite a large amount of between study variability. So these are not particularly restrictive prior distributions. So we're going to go ahead and fit this model in WinBUGS. And to do that, what I'll do is I'll step through the model here, and then we'll actually go into WinBUGS and fit the model quickly. We'll start here with our model for the data. And so this says we'll have so the way that we'll imagine that we're setting up our observed data here, we'll call it OS_tran for transformed. That's because I've already applied the logit transform to the observed data. So these are gonna reside in a matrix that's gonna have one row for each treatment arm, and it's gonna have one column for each of the observed time points. So in this case, because I have up to four observed time points, I'll have 4 columns in my data matrix. And the number of arms here turns out to be 34, 2 times 17 studies. So this OS_tran is a matrix that's 34 by 4. So what we're saying here is that the vector of observations for the ith treatment arm follows a multivariate normal distribution where the mean is mu_tran and the variance or the precision matrix, is this prec.os. Prec.os now is a 3-dimensional array where we're taking the first element of that. And when we get into R, we'll see more closely what this looks like. But each of those elements for each treatment arm is going to be itself a 4x4 matrix. So that is, this prec.os is the inverse of this VIG. We have to use things in terms of inverses in terms of precisions, which are the inverses of the variance matrices, because that's how WinBUGS parameterizes the normal distribution. So this is our basic model for the data, and this line of code here corresponds exactly to this model here, this logit model here. And then we'll define what this mu_tran is. Well, mu_tran is going to be the logit of mu, and mu is just our model. I could have called this capital S, I suppose. This is our model, which is e to the minus lambda times time. And here I've scaled time to be in terms of years. So our lambda will be the event rate per year. And then this part here says, well, the lambda for study arm I is just the exponential of a log lambda for the ith trial plus a log delta for the ith trial times an indicator for whether the treatment group is treatment group 2, which in this particular data set is going to correspond to the radiochemo group. And then we incorporate the between study level effects here. So we'll define this as it looks like a loop over the n trials. And for each trial, we'll say that the log of the lambda 0 comes from a normal distribution with mean mu lambda 0 and precision lambda 0. And similarly for the log deltas, they come from a mean with mu delta and a precision prec dot delta. And then down here are our prior distributions on the overall mean lambda, the overall mean delta, the between study standard deviation for lambdas, and the between study standard deviation for deltas. That's really all there is to fitting this model in WinBUGS. So the writing the bugs code itself looks fairly straightforward, and there's a little bit of work to do to set up the data, and that's what we'll look at in R. So let me see real quickly if there are any questions before we jump into the R code. Okay, I don't see any questions. So I think what we'll do now is I'll go ahead and we'll fit this model in real time, and then take a short break. So I posted to the course site the files that you'll need to recreate the analyses I'm doing here, as well as to do your homework. And for this particular example, we'll use this code called meta-analysis survival model. The first couple of things we need to do are we're going to load our R to WinBUGS package and the lattice package. And we'll get a couple warnings here because this version of R to WinBUGS I have here is built under R 2.15.3, and we're using R 2.15.2. I use in my code here a package called reshape. If you're using your own R installations, you may well already have this package installed. Unfortunately, I wasn't thinking ahead of time, and so I didn't include it in the bundle of packages that came with the USB for this course. So if you are working off the USB for the course, you'll need to install that. I've already done that, so I'm not going to reinstall that. But then you will need to load the reshape library as well. So let's just check our working directory to make sure we're going to be working in the right place, and if you're not, to set it to the directory where you've saved the data. So we'll read in this data, which is I've called the file findsurvival.csv. And if we look at that, well, I'll just read in the data set and we can look at it in R. We run that and look at that data set. We'll just look at the top few rows of that. It looks like this. So we have variables trial, arm, which is just a numeric 1 or 2. Trial is a numeric that runs 1 through 17. We have a variable called endpoint, which is either OS for the survival times or SE for the standard errors. Then we have 4 columns, M6, M12, M18, and M24 for the survival times at 6, 12, 18, and 24 months. I'm sorry, those are the surviving probabilities. Or surviving percents, actually. This is what we're going to model. We're going to need to kind of do a little reformatting of the data to put it in a useful format for the kinds of models that we're going to fit. But first, before we do that, let's create a treatment factor, a treatment indicator. And then we're going to use the melt function, which is in the reshape library, to kind of put this from a horizontal sort of data set into a vertical kind of data set. And so the 2 lines of code here do that, and then create this variable called time that we'll use for running our model. So if we look at now what the head of this data set called DM looks like, it looks like this. So now we have our trial indicators, 1 through 17, our treatment variables, which are a factor here. It's either radiotherapy plus chemo or radiotherapy. Our endpoint, again, OS or SE, and then these values, which correspond to the value of OS or SE. And this time variable was created from, which the time point values. So if we want to plot that, we can use this dataset DM to plot our data, and this would correspond to the plot that we have in the slides. So what we want to do in order to work with this particular data set is we want to extract the standard errors and the survival times apart from each other. And because they're in percentages, we want to convert them from a 0 to 100 scale to a 0 to 1 scale into a probability scale. So to do that, we just divide those by 100. So now we have, for example, our data set OS has look just like the previous one, but now we've got these things here on the 0 to 1 scale. And now what we need to do, the next chunk of code, what that's doing is it's creating our precision matrices that we're going to feed into R. And this is a kind of a fairly long bit of code to do essentially to do the calculations that are shown on, let's see, on this slide here. So the next chunk of code is essentially calculating the variance covariance matrices VI and then inverting them. And it's calculating those VIs using the standard errors and the observed survival probabilities. And so that's what this chunk of code here does. What it does is for each row, that is for each treatment arm, it extracts the survival times for that treatment arm. If any of them are missing, it does a little bit of imputation there. That's because it's conceivable that you may not have all studies having the same time points. Like here, study 17 is missing the month 6 and the month 18 time point. But all of these matrices themselves need to be 4 by 4. So we need to do a little bit of imputation there. And then we extract the standard errors in a similar way. Do some imputation if the standard errors are missing, again to get an approximation for the time points that have missing or non-observed survival times. Then this little bit of code here calculates the correlations. And then we need to do a little bit of manipulation in order to make those correlation values into a symmetric matrix. Excuse me here. Let's pull up WinBUGS again, and I'll show you. I'm sorry, let me pull up the slides real quickly and show you why that's important. So, if we stare at this correlation piece here in the middle, if k is greater than, if time point k is greater than time point L, then S hat has to be less than or equal to, or S hat at the kth time point has to be less than or equal to S hat at the Lth time point. So for k greater than L, this thing is going to be less than 1. When k is less than L, we need to take the reciprocal of that. So this, the chunk of code kind of manages all of that for you. And then what it does is it turns those correlations and standard errors into a variance covariance matrix, and then takes the solution or the inverse of that to come up with a precision matrix. So this chunk of code is doing all the work for us to calculate those VIs. And so if we were to look at one of these, if we were to look at prec.mats, if we look at the dimension of that first, we see that it's an array that has 34 by 4 by 4. And so we have 34 treatment arms, and each treatment arm is a 4 by 4 matrix. So if we want to look at the precision matrix for the first treatment arm, we would look at something like that, and it looks like this. And if we wanted to look at what that corresponding variance-covariance matrix looks like for that treatment arm, we could take the inverse of that. So the variance-covariance matrix looks like that. Because I've rounded these to the precision matrices to 4 decimal places, these are symmetric, but they're due to rounding error. We get things here that may not be exactly symmetric. But let's see if we can still get the cove to core function to work, which will convert this covariance matrix now to a correlation matrix. Okay, so we can see here for treatment arm 1, which is the radiotherapy group in study 1, that is the blue time point, the blue observations here in this lower left-hand panel. The correlation between the first and second observation is about 0.5, between the second and third observations about 0.4, and between the last 2 observations is around 0.85. And in fact, what I didn't point out, what I didn't highlight here is I put in a little bit of code in here that truncates the maximum amount of correlation to be 85%. And that's because if you have 2 observations that are very, very close, like here in study 9 in this blue curve, that the survival estimates were essentially the same, the correlation ends up being something that's 99%. And when you do the inversion to get a precision matrix and pass that into WinBUGS, you get things that are very numerically unstable, and you can run into errors. So again, we think about these precision matrices as being kind of working precision matrices or working variance-covariance matrices that are giving us a pretty good approximation for accounting for the correlation of time points, of observations within treatment arms over time. So it's something that should be better than treating them as independent, but not accounting entirely for exactly the amount of correlation that's really there. So we have this data object now called PrecMats. It's this precision that'll get passed into WinBUGS as some data. Here's just defining the logit function that I'll use to then take a transformation of my survival data. So now I'm creating some data that I'll pass into WinBUGS, create this list called OS data. The data that I'll pass in will be the number of arms, the number of trials, the maximum number of observations per arm, the logit transform survival probabilities, a trial indicator, a numeric treatment indicator. This is going to be 1 or 2. Trial here is going to range from 1 to 17. We'll have a time vector and then our precision array. Because we have some missing survival times in study 17, we're going to need to specify some starting values for the MCMC algorithm for that. And so here I'm just imputing those as taking the mean between 2 time points. So the mean between these 2 time points to get the observation of times 18, and the mean between 1 and around 50% to get the mean at 6 months. You don't have to do this, but it gets the Markov chain started out in a good spot. And here's just a function then that will give us some initial values for the parameters that are of interest in the model here: overall mean of the lambdas or overall mean of the deltas, the between study standard deviations of lambdas and deltas. And then I'm also passing in here the imputed values for the survival times for the study that has the missing observations. So we'll go ahead and run that, and then tell it the parameters I want to monitor, which in addition to the 4 basic parameters of the model, will monitor the individual study level estimates of the log of lambda and the log of delta. And then we'll go ahead and fit the model. In this case, I'm going to run three Markov chains. For each one, I'll do a burn-in of 10,000 iterations, and then I'll follow that with 30,000 iterations for a total of 40,000 iterations from each chain. This particular model might take a minute or so to run. So while it's running, I'll see if anyone has any questions. So the model's now finished its burn-in phase. It's moving on to the post-burn-in. And then this will wrap up here in just a second. And then we can, once we get it back, we won't look at any particular diagnostic plots. We'll take one sort of pass at looking at how the model fits the data. And then sort of ask ourselves maybe whether we could come up with something better. So now let's finish the MCNC part, just writing the coda files out, and we come back to R. So it's still now R to WinBUGS is reading in those the output from WinBUGS and creating all those objects that we get in our fit here called fit1. So let's go back to that data set DM that had that sort of transposed version of the data, and fit overlay to the observed data the model fits. And by here, what I mean by model fit is I'm going to take the median, the posterior median of the lambdas for each study, and the posterior median of the delta for each treatment arm, or for each study, and then overlay those posterior predicted median values on top of the data. So I'm not attempting to create any sort of credible intervals here or anything. I'm just overlaying the posterior median values. And if we do that, we get a figure that looks like this. And this same figure is reproduced in the slides. So why don't we jump back to the slides and look at it there where it's a little bit bigger. So here's that same figure. We have the data are the red and blue dots as before, and the red line is the median prediction for each of these treatment arms for the radio plus chemo combination, and the blue lines are the predictions for the radiotherapy alone observations. And I'll give you a second to kind of stare at that and think about whether you think this particular model fits the data. Seems to me that when I look at this particular model, again, we're assuming these are exponential survival curves, that if we look at the early time points, the model is consistently underpredicting the observed data. We see it clearly here in study 14, in study 13, in study 12, in study 7, which gives us some indication that we probably want a model that has a little bit more curvature. It's kind of lower hazard at the beginning and then an increasing hazard over time, rather than a model that assumes the hazard is constant over time, which is what this exponential model assumes. So it's probably the case that some other kind of model should give us a better fit. So that's going to be your homework, is to take the model code that I provided to you for fitting the exponential model and fit some sort of alternative survival model. Could be a Weibull model. That might be where I would start. Could be a Gompertz model. It could be a log normal survival function. All of these models have an additional parameter that allows that shape to vary. And I might suggest that you would at least start with allowing that shape parameter to vary across studies, but be shared within a study, so that you may have a Weibull model that's got a shape parameter of 2 for study 12, but that shape parameter would be 2 for both the radiotherapy and the radio plus chemo group. But in study 13, it might be 3. So we'll have some between study variability in that. And you may also, if you have time and interest, want to compare the results to a model that does not account for the correlation within a treatment arm, and then see how your posterior inference for the overall treatment effect changes. Particularly, you may see changes in the central tendency, but you'll you'll also see changes in the uncertainty in that. And when we're not accounting for the correlation, the implicit assumption there is that we have more information than we actually do. And so you'll end up with what should be tighter credible intervals. So in modifying the WinBUGS code, really what you'll be doing primarily here is, let me open up that code for you real quick. What you'll be modifying there is this bugs model file, which here is called exp model. Ooh, that doesn't look good. Let's open it up in R. Maybe we'll get a better rendering of that. So here's our bugs code. I showed you on the slide previously, but here it is in the text file. Really all that we're talking about doing is we're changing this part of the model here from an exponential kind of model to a Weibull model, for example. And if you're not familiar with what the Weibull survival time is, just feel free to ask, and we can post that survival function on the wiki. In addition to allowing between study variance and the two scale parameters, you'd add in an additional parameter here that would allow between study variability in that shape parameter. If you wanted to do Gumpert's or you wanted to do log normal, this is where you're really modifying that model. Otherwise, pretty much all the code is going to stay the same, as long as we're sticking with this logit transformation. If you wanted to use a different transformation, then you'd need to come back to the R code, and you need to modify this code here that's deriving those precision matrices. Okay, so why don't we take a short 5-minute break? We'll convene back at 1/4 after the hour, 15 minutes after the hour, and we'll finish up by talking about the Uvens and Janssen approach to modeling survival data. And of course, during the break, if you have any questions, feel free to post them. Okay, let's go ahead and we'll get restarted. So there's a question here from Mike that said, asked did you say that survival can increase between time points? If so, doesn't that go against survival function assumptions? Um, you're absolutely right. That does go against survival function assumptions. And if I said that, it was unintentional. Um, what where I may have said that was when we were, or said something along those lines, was when I was discussing this correlation here. And the survival function at a time point tk greater than time point tl should always be less than or equal to, so Sijk should always be less than or equal to Sijl for time point k being greater than time point l. When time, because the correlation matrix needs to be symmetric, if you simply flip this equation around, or the way that it was defined back here on this slide when we were talking about the deer approach. Oops, that's the Aaron's model. Here this says for Tijk greater than Tijl, we have this definition. What this isn't providing you is a definition for when Tijk is less than Tijl. And if you were to plug into this particular formula for the kth time point less than the lth time point, you'd end up with a correlation that's bigger than 1. So what you need to keep in mind is when you're constructing that correlation matrix, this is the appropriate formula for time points k greater than L. You take the reciprocal of that for time points k less than L. And in describing that, if I said that the survival time is bigger, can be increasing, then, or the survival function could be increasing, then I apologize. So we're going to continue now to talk about modeling of survival times, but we're going to look at a different approach that was published recently by WinBUGS and Jansen. And let me go ahead and move here to full screen. Make sure that I'm showing my screen and everything here. And so their approach was said, rather than doing what Aaron's and Deere did, which was model the observed survival times, observed survival functions, they said, well, let's, and because those are correlated over time, rather than doing that, let's take distinct time intervals, non-overlapping time intervals, that covers the entire span of time in a study, and model the number of patients that have events in those intervals. And over time, those time intervals, those number of patients having events, are going to be independent. And so we don't have to worry about this correlation issue. And they actually developed their model in the context of a network meta-analysis. But I'll show you how we can apply this same approach in a model-based meta-analysis framework. So let's start with the example that they use in their paper. What they do is they present data from 6 clinical trials that compare 3 different treatments for multiple myeloma. And in the example that I'll show you in class today, we're just going to focus on 5 of the studies. And in those 5 studies, they compare melphalan and prednisone, which they denote by MP, with the combination of MP plus thalidomide. And all of these 5 studies were conducted in patients that were not eligible for bone marrow transplant. And the objective of their particular analysis was to compare the overall survival across, this meta-analysis was to compare the overall survival, so that's our endpoint, across first-line treatments, that's MP and MPT, in patients that were not eligible for transplant based on randomized controlled trial evidence. So this is giving us sort of, as we talked early on about the PICO, the population, the interventions, and the outcomes. So here's the data that they published in their paper. The red dots are the survival times for the MPT group, and the blue dots are the surviving fractions. I keep saying survival times. I mean surviving fractions for the MP group. So we can see in some studies they seem to be pretty much the same, and in maybe 2 studies there seems to be a slight benefit of adding thalidomide to the MP regimen. Now, actually, in their paper, what they published is all of the numbers of events and number at risk in each time interval, and from that you can actually work backwards and calculate the observed fraction surviving. That's what I've done here to make this plot. So what they do is they say, let's imagine, so again, we'll use the similar notation we had before, that the proportion of subjects alive at time tj is given by S of tj. So S is our survival function. Then it's pretty simple to show that the number of subjects who are alive at time tj, so that's our risk set, the number of patients, among the patients at risk at time tj, among those patients who die between time tj and time tj plus 1, so that's between within that time interval, we can model that using a binomial distribution, where we have the number of patients that die in that interval is rj, follows a binomial distribution, or the number of patients who are at risk for death is nj, that's the number of patients at risk at the beginning of the time interval, and the probability of dying in that interval is pj. And just from basic, for introductory probability theory, we can show that pj is equal to the survival probability of time at the beginning of the interval minus the survival probability at the end of the interval divided by the survival probability at the beginning of the interval. So this is really the conditional probability of dying in that time interval, given that you're alive at the beginning of the time interval. And the fact that the way that we're defining these intervals in that way and using these conditional probabilities is what makes the number of patients dying in each interval across time independent. So this was a really neat trick, and allows us now to come up with a model for the S's, just like we did before, a model for the survival function. And if we can extract from the paper the R's and the N's, then we can go ahead and move forward with our analysis. And for now, we'll just assume that we can do that without too much problem. We can get the number at risk and the number of patients having events in any interval. And given those data, then we can we can fit this sort of model. So let's think about we're going to fit a model here to the data from these 5 studies. And again, we'll just start with the simple exponential survival model. So this looks very much like what we used in the previous example. So we're modeling the survival time in study I, treatment group G at time t, as following an exponential survival model. So that's e to the minus lambda ig times t. Just like before, the log of the event rate in treatment group G in study I is mu I plus delta I times an indicator for whether, in this case, the treatment group is the MPT group. So notice in both cases, the mu I is the log hazard for the reference group, and mu I plus delta I is the log hazard for the experimental group. And just as before, we allow our mu i's to come from a population of mu's that are centered at mu bar with between study variance omega squared mu, and the log hazard ratios delta I come from a population centered at delta bar with between study variability omega squared delta. So in this case, we only have 5 studies, so it's a relatively small meta-analysis. And you can think about what kinds of problems that might cause, and maybe we can discuss those if we have time at the end of the lecture today. So again, I just chose to use the same sort of reference priors that I used before for the overall mean log event rate in the control arm and the log hazard ratio, as well as the between study variance in the log event rates in the control group and the log hazard ratios. So fitting this model in WinBUGS is actually, again, pretty straightforward. What I'll do is I'll review the code here, and then we'll go into R to fit the model in real time, just to show you what we need to do in terms of R to set things up. So here our model says that we have in this case, we're gonna have a vector. Our data is going to be a vector, and the vector is going to be the variable R is going to have one observation for every time point in every treatment arm in every study. So it's going to be a vector that's going to have one observation for each of these dots in this figure, and each of those number of patients dying within that time interval is going to follow a binomial distribution with probability pi and number at risk ni. And pi is just going to be the survival function at the start of the time interval minus the survival function at the end of the time interval divided by the survival function at the start of the time interval. And because we're using an exponential model, we know that the survival function at the start of the time interval is just e to the minus lambda I times the time at the start of the interval. And this is going to be data. This start will be data that will pass in. And the survival function at the end is that same functional form, but now for time, we'll plug in the time at the end of the interval. And again, that'll be data that will pass into WinBUGS. And just as before, we have our same sort of model here for the log of the lambdas. So this little bit of code here is just defining defining this binomial likelihood here and the first two lines of code, the first two lines of the model here. And then just as before, we have our model for the between study effects of lambda and delta. And then our prior distributions for mu lambda, mu delta, omega lambda 0, and omega delta. So really the core of the model here that's different from what we fit before was just here how we're defining our likelihood. So let's go switch over to R and look at how we might set up the data and then run that particular model in WinBUGS. So we'll close out these things here. And we'll remove all the objects we created when we ran our first analysis. Now the code for running this is in a file called myeloma survival. Again, that's in part of the zip file that I posted to the course website earlier today. So again, we'll load in a few libraries that will be useful for us in our analysis and set our working directory to the location where the data is residing. Now let's read in our data, and we're going to subset that data set only to include the first 5 studies. So if I look at the data that is in our data file, it looks like this. So you have a study variable that's going to go from 1 to 5. I have an author variable here that I just added in to make the plot labels look better. We have a group, which is just going to be MPT or MP. We have the number of patients dying in a treatment interval, the number of patients at risk in that treatment interval, the time of the end of the treatment interval, and the time of the start of the treatment interval. Okay, so this is all of this data, the study indicator, the treatment group, the R, the N, the start and the end are going to be data that will pass into WinBUGS. So in order to put our data in a, well, I'll skip this part here. And if we wanted to derive the Kaplan-Meier version of the survival function from the number at risk and the number having events, that's really what this chunk of code here is doing. Not this piece of code. This just creates a treatment arm indicator. But this bit of code here creates a data frame that calculates what is the survival function at each of these starting time points for each interval. And so if you had this sort of binomial data and wanted to derive what the surviving fractions are, that's code that you would use to do that. But we're really here to fit this binomial model. So what we want to do is set up our data for our bugs model. So we'll use this data set D2, and we'll pass in the number of observations, which is just equal to the number of rows in that data frame. The number of studies is going to be 5, so it's the number of unique studies we have in our data frame. R is just R, N is the number at risk, study is our study indicator, and start and end are just the same as start and end. And then we'll create a variable group that's a numeric version of this factor variable here. So we'll just create that list that we'll pass into bugs. In this case, for the initial values, we'll set up initial values for, or a function that generates initial values for mu lambda, mu delta, omega delta, and then for each of the study-specific lambdas and deltas as well. Again, you don't really have to provide initial values for the study-specific parameters, but it gets your NCNC chains kind of going from a reasonably good starting point. And then we'll just monitor all of these parameters that we've defined initial values for. And then fitting it again, I'll run 3 chains. I don't have it explicitly specified here, but it runs 3 by default. I'll run a total of 12,500 iterations and a burn-in of 2,500 for each Markov chain. It seems about adequate for these models after a little bit of tinkering. So this model runs actually pretty quickly. So we've already made it through our 2,500 iterations of burn-in, and now we're into the post-burn-in samples. And this will finish up here pretty quickly. Well, that's wrapping up. I'll just check to see if anyone has any questions here. Okay, Mike, thanks for letting me know that I answered your question. Okay, so Bugs is finished fitting our model. We didn't do any diagnostic plots in the previous version of the model. I know that you've looked at lots of diagnostic plots and have code for diagnostic plots that Bill's covered. There is one function. If anyone uses the ARM library, it's a library that goes along with the multi-level regression modeling book by Jennifer Hill and Andrew Gelman. They have a pretty useful function in there called traceplot. I've exported that function here, and I've included it as a source code in the files that I've provided to you, so you don't have to have the ARM function if you don't already have it. And what that allows us to do is to take a fitted bugs object like this fit1 and just pass that into this function. I've renamed it bugs traceplot, and then tell it what the layout is to be. Before I run that, let's see if we can turn on our history here. You could output this to a PDF file if you want. It's probably easier to do it that way. Or if you run this bugs traceplot, you get what it's doing is it overlays the trace plots from each of the 3 Markov chains that we've run. And I think I've saved that. Let me just make sure. I think I've saved that into a PDF. Yeah, here. So you can see that from our that burn-in seemed to be adequate. We get pretty well converged Markov chains, and there are a few little spikes here and there. See we mu lambda spiking up to some big values, and omega delta we get some fairly large values, up to maybe 8 or 9. But the bulk of them are kind of centered down here at relatively small values. So that's giving us some clue that our priors weren't restrictive in really in the sense that our posteriors are well within the boundaries of what our priors are enforcing. And then there's also a little bit of code in that in the R function to create some density plots here. But I'll leave that to you to run those diagnostic plots when you get to your homework assignments. So we can look at our posterior fit here. If we look at our summary of our fitted object, we see that the baseline log hazard ratio for the MP group is around minus 0.39. The mu delta is around minus 0.2. So that's saying that there's that the average log hazard in the MPT group is the mu lambda 0 plus mu delta, so that gives us something that's about minus 0.41. So in the context of survival, a lower hazard is better, so this is saying that the survival curve should be shifted out to the right. And we have a median between study log event rate of 0.2 and a median log hazard ratio of standard deviation of 0.2. So there's some between study variability in those elements as well. And then these last pieces here are just our estimates of the study-specific deltas and lambdas. So we can use all of that to make a plot. And so I'm just going to make a simple, fairly simple plot here that overlays the observed data with a, in this case, I'll overlay some shaded polygons that provide 90% credible intervals. And I'll flip back to the slides to look at this in a little bit bigger format. But just to quickly review through the code, so we're plotting our data object D2 here. We're plotting the survival by the start time, or survival versus the start time by each study. And then each panel is doing a little bit of work here to calculate the posterior median and posterior 5th and 95th percentiles over time. That's kind of what all this machinery is doing here. And then these last few pieces here are just actually plotting out those credible intervals in the data. So we'll jump over to the slides here to look at the results of how the model fits the data. And then we'll come back to see what are the kinds of things we can extract from our model. So these data seem to fit a little bit better than the exponential model seems to fit these data a little bit better than the exponential model fit to the glioma data we looked at previously. And we get reasonably good fits, not terrific fits to the survival data here. What I'm not showing you is we could calculate the probability of death in each interval and plot that versus the observed probabilities of death in each interval. That would be another kind of diagnostic plot. And you could, if you're interested in making that, you can add it to your homework. And if you try to make that plot and aren't able, feel free to post to the course website, and we can work through how to do that. But there does appear there may be a little bit of model misspecification here in the Fécond study, maybe here in the Goldbrenson study, and so there's a little bit of room here to possibly improve the model, but also recall that the data that was published in Neuvin's paper includes data for a 6th trial, and that 6th trial compared MP to cyclophosphamide, thalidomide, and dexamethasone attenuated, which is, they abbreviate in the paper, CTDA. So for the second piece of this time to event homework, what I'd like you to do is refit this kind of model, but include the data from that study. And the data from that study is in the data set that I put together for you. And so I'd like you to make the comparisons between CTDA, MP, and MPT. and then evaluate along the same time whether you think this exponential model is a reasonably good fit or whether you think you should fit something that's a little bit more flexible like a Weibull or a Comfort's model. So the way that you might want to make comparisons between treatment groups is to look at maybe the hazard ratio or the predicted median survival times or something like that, or the difference in median survival times. In this case, the hazard ratio is just for this particular model, this exponential model, the hazard ratio is just e to the delta. And here what I'm looking at is the population average, the mu delta being my sort of population average log hazard rate. So if I extract those values and then maybe plot make a density plot of those. Let's reset my graphics device. And then learn how to spell MFRO. Now let's make that plot again, and it'll show up a little bit bigger. So, so if we do a density plot of the hazard ratios, we get a plot that looks like this. And it looks like there's kind of a lot of information here spiked up between 0 and 2, and there must be some observation out here around 14 or so. That has maybe just 1 or 2 observations out here, and that's why we're not getting much of a density plot out there, but that the plot itself runs out that far. And in fact, if we look at a summary of these hazard ratios, we see that the posterior distribution our samples run from about minus 0.07 to about 13.9. But the bulk of the probability mass, bulk of the mass of the distribution here lies between about minus 0.6 and 1.2, 1.21. That would be a 95% credible interval for the hazard ratio. In this case, a hazard ratio less than 0 would be evidence of a hazard ratio less than 1 would be evidence of a beneficial effect of adding thalidomide to NP. Based on these 5 studies, there's maybe some evidence that our central tendency of our posterior is less than 1, but if we wanted to calculate say a Bayesian p-value, we might look at what is the posterior probability that the hazard ratio is less than 1. And so a Bayesian p-value, here would be about 1 minus that, or about 0.12 or 12%. So it's not very convincing evidence that we have an effect on survival, and even if it is, it's estimated to be a sort of a modest benefit. If we wanted to zoom in here on our density plot, we could do that by only restricting our density estimation from around 0.25 to 2, and that kind of zooms in on our density plot we had before, and we see a posterior distribution that looks something like this. So again, we see the bulk of the mass is less than 1, bulk of the distribution is less than 1, but there's about 12% of this tail area here that's above 1. And if you felt like you really needed to have a meaningful benefit of at least 20% reduction in hazard, you might want to ask yourself, what's the probability that the hazard ratio is less than 0.8? And if we were to do that, we could get a probability. There's a 35% posterior probability that the typical hazard ratio is less than 0.8. So these are the kinds of summaries we can do from fitting these survival models. Okay. So your homework is going to be to do a similar kind of analysis, but bringing in that 6th trial and making comparisons in addition to between NP and NPT, make the comparisons to CTDA. Okay. So we've got these two approaches, and you might be wondering, well, which one would I recommend that you use? And I'd say, well, we maybe want to start by thinking about what the assumptions are that these two different approaches make. This Uvens approach, maybe on the surface of it, might appear to make fewer assumptions. We don't have to have these standard errors of the S hat. So we don't have to have assumptions about correlation over time. We're not having to pick some arbitrary choice of transformation for the survival function. But we have to recognize that there are assumptions underlying this approach, and I've kind of glossed over some of them. And in particular, they relate to how do you calculate the number of events in those intervals, and how do you calculate the number of patients at risk in an interval. Now, the number of patients, if you know the number of patients at risk in an interval, and you know the survival curve, you can actually back calculate the number of patients having an event in an interval. So really, the crux of the issue with this approach is that you need to make some assumptions about censoring, and that in terms of how they're impacting the number of patients at risk in each time interval. There's also, I guess, an issue about how do you chop up the time intervals into, how big or how small do you make them. But putting that issue aside, we have to make some assumptions about censoring. In the Uvens paper, what they do is they sort of either assume it to be non-existent, so assume that there's no censoring, or they say you can assume that all the censoring occurs before any of the events occurred. And they give some algorithms well, in the case that there's no censoring, then calculating the number of events is a straightforward function of the number at risk and the survival function, both at the beginning and at the end of the interval. But if it's not, then they give some formulas for deriving that. And so we're going to get the most reliable estimates or guesses at the number at risk when we have some information about the number at risk over time. So if we have Kaplan-Meier plots that provide for us those number at risk, like this one here at the bottom, then we can say, well, we know at the beginning of an interval starting at time 48 months, there were 17 patients at risk in the MP group, and there were 26 patients at risk in the MPT group. So that kind of grounds us at these various time points. If all that we know is the number of patients at risk at the beginning, and we're not provided these kinds of tabulated number at risk over time, then we're on a lot more shaky ground in terms of we really need to rely very heavily on assumptions. And what they generally say is, well, we'll just assume that there's no censoring at all. For lack of, and the argument is, well, that's one assumption and it's just as well founded as any other assumption. But you could imagine using some other assumption about censoring mechanism and censoring rates. So, my recommendation is generally, it kind of depends on what data are available to you. If you have those numbers at risk over time, then I would generally tend to use the Uvens approach. They do, as I mentioned, provide some algorithm for calculating the number of events in a time interval. That's a very straightforward function. And there's also a more recent paper I mentioned here by Guyot that gives us a secondary algorithm for calculating both RJ and NJ, the number of patients at risk. If you don't have those numbers at risk over time, then it's kind of a toss-up, I think, as to whether you want to use the Aaron's approach or the Uvens approach. Both, I think, at that point are really you have to make some implicit or explicit assumptions about censoring that could be very impactful in terms of your analysis. And you can imagine that if you have both of these approaches, at least the way that I'm presenting them is we're really modeling that underlying survival function as some parametric model. And so if you have some papers that provide number at risk and other papers that provide maybe some standard errors from your Kaplan-Meier curves, it would be fairly easy to do some sort of combined approach if you wanted to. But by and large, I think this sort of Uvens approach seems to be the most easily implemented and and probably given the data that we're likely to get from publications in the literature. So that's what we all wanted to cover today. Let me make sure. Yeah, so we'll stop with the lecture there. Let me just see if we have any new questions. Okay, so Dana was asking, so far in these examples, censoring is ignored. Can you comment on why that is, and if censoring would be an issue in some circumstances? Okay, so you're right. So I think I covered that a little bit there, kind of in the sort of final bit about which approach to use. The assumptions about censoring can be pretty important. The argument that they make in the WinBUGS paper for assuming that all the censoring would, given that you get these number at risk over time, and assuming that all the censoring happens before any of the events happen, the argument is, well, that makes the number at risk smaller, which translates into more uncertainty in terms of your probability of survival within that interval. So the handling of censoring there is to say it happens and then, but assume it happens all before any events happen. What's interesting in their case, and we didn't really, let me see if I can pull it up. So in the papers, for example, in this paper here, this Kaplan-Meier plot is from one of the papers that they use in their analysis. You can see that the paper provides numbers at risk at baseline, at 6 months, 12 months, 18 months. So the numbers at risk come in 6-month intervals. Whereas what in the data set that they provide for us, they extract data in 3-month intervals. So they calculate number of events over the 0 to 3 months, number of events between 3 and 6 months, between 6 and 9 months, and so on. So in doing that, they're making some assumption about censoring in between these points where they have information. And their assumption there is they're kind of using these points at which they have information and kind of working backwards in between, making the assumption that any censoring happens before any events. It's a crude approximation, but honestly, it's hard to know anything better, really. You could imagine trying to model that if there's some information about dropout rates in the papers, but yeah, the issue of censoring is a hard one. In particular, if you're not given these numbers at risk over time, and quite honestly, it's probably going to depend on the disease area that you're working in and the journals that you're extracting papers from. Some journals are very fastidious about requiring those numbers at risk to be in every Kaplan-Meier plot, and others are not. And so how often you are able to get the information that you need may depend on the disease area that you're working in. In terms of the Aaron's approach, where censoring comes in, again, censoring is going to come in our standard error. In the fact that the standard error or the variance of the Kaplan-Meier estimator depends on the variance of the cumulative hazard, and the variance of the cumulative hazard is depending on the number at risk over time. And so if you had those numbers again at the bottom, we could use those to derive some standard errors using these formulas. That's what's talked about in the paper by Parmar. So again, we have some information about censoring in that through that, but again, without that information, we have to make some pretty important assumptions. In the paper by Guyot and colleagues, what they recommend is they just recommend using this approach, just essentially ignoring censoring altogether. So hang on and see if there are any other questions for another minute or so, and otherwise that's the end of the material for today. The questions are posed that I've asked you to work on for homework are in the slides here. The homework 1 asks you to fit additional, more flexible models to the glioma data, and the homework 2 asks you to fit this same exponential model using the WinBUGS approach to the multiple myeloma data, but now adding in that additional study. And all of the material should be already posted to the website. I think Bill mentioned that the midterm exam is coming, and it's in process of being made right now, and he'll post an update for everyone about when that's ready. So over the course of the week, if you have any questions, feel free to ask during the lab session on Monday. We can maybe cover some of those if any questions come, and in the absence of those, we'll work through the homework problems. So, oh, I see there was one other question. Thanks, Dana. Question is, are there sensitivity analyses that could be useful in determining an approach or for checking the censoring issue? Well, certainly you could imagine a sensitivity analysis where you assume there is no censoring. So if you're using this WinBUGS approach, it would be assuming that the number at risk is simply given. There's no censoring in between time intervals, and all of the changes in numbers at risk are because of events happening, or that all events happen before censoring. I guess that would be the same assumption. And contrast that with all the censoring happened before events happen. If you're working in with the Aaron's type model, then if you don't have standard errors, you need to derive them. Then let me find my piece here on that. Then essentially, what you could imagine doing is having some. The sensitivity analysis would probably be to have some model that is some assumed parametric model for additional dropout over time or something like that. That's going to be completely guesswork, because without that information, you're going to just have to kind of make something up about the hazard. And you could look at the sensitivity to different choices for that dropout sort of model. Other than that, I don't have any particular diagnostics other than fitting a couple of different models with different assumptions about sensory mechanisms and then seeing how sensitive the results are to those. So thanks for hanging in there, and I will talk to everybody on Monday. I hope you have a good weekend.